Hello guys, this is CodeNCode and this is video editorial for the problem chef and round run taken from Codechef. And this problem we are going to solve as a practice problem from first strongly connected component algorithm, that is Kosa-Raju's algorithm that we have just finished a week ago, I guess. So this is the problem that we are going to solve using Kosa-Raju's algorithm for strongly connected component. You can try and read this problem and try to find the solution yourself. The official editorial does not solve the problem using a strongly connected component. You can solve the same problem using different methods. There are many to solve this problem, but we will be solving this using strongly connected component because of course we need to practice SCC, as we have just studied implementation of Kosa-Raju's algorithm. So this is just for practice. Now chef has n boxes and each box contains some food, so they are arranged in clockwise order. Yeah, so first, second, third, fourth and so on. So they are arranged in clockwise order. Each is having infinite amount of food, and then its tastiness is defined by value AI. There's nothing to do with the tastiness here. It simply tells you how many boxes you need to leave to get to the next one. Basically all of them are arranged in circular clockwise manner, first one being here, then the second, then third, so on. N and 1 are of course placed right next to each other, like this is the nth and this is the first and so on. So what chef does, a chef has defined a definition of magic box. So a magic box is defined by these rules. First, chef picks any box I and of course eats food from it, and then since that box has n value, have a value AI defined with it. So what you have to do, you are standing at ith box, in front of the ith box, then the value, you know the value AI, this is given in the input, and then you leave the next AI boxes and reach the other box. So basically if there are say 5 boxes, 1 2 3 4 and 5, and you are on the second box and AI value is 2, so you are on the second box, you will leave the third and the fourth, and now you are at the 5th box. So you were at second box, AI was 2, you will leave the next 2 box and you will reach the other box. So you will leave the third and the fourth box and you will reach to the 5th box. So this is the operation. So now chef eats the food from the ith box and skips the next AI boxes, and of course they are arranged in circular manner. So when you are on n, from n you will reach 1, right? Now the chef is staying in dash 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 box. Box I is magic box if at some points of such game started at box I, and chef will find himself staying in the front of the same box again. Basically when you started from say ith box and after certain operation you are again standing in front of box I, if that happens then box I will be called magic box. So basically you are given n and AI values and you have to tell how many magic boxes are there. This would be easy to understand when I explain you with an example. So there are 3 test cases. The first test case contains 4 boxes, 1 1 1 1. So these are the AI values. So if I show you the graph of it, you can of course make the graph of it. So I'm using the 0-based index system. So this is the 0th node, first, second and third node. There are 4 and all of the 4 are arranged in circular clockwise manner, but since I'm using graphical representation of that, I do not need to represent them in circular manner, but we'll be following all of the rules of that. So the first AI, starting from 0th node, you need to leave the next node. It says AI is equals to 1, that means you need to leave the next node. So from 0 the next node is of course 1, so you leave 1 and from 0 you would reach 2. That is why there is an edge from 0 to 2, because from 0 you will leave the next node and then after that you would go to this, right, after leaving the next node. So from 0 there is an edge to 2, from 1 there would be an edge to 3, and that is why there is an edge from 1 to 3, and from second there is an edge to 0, because from second you would go to third, and from third you would reach to 0, because from second you need to leave one box, so you left this box and then you are at this box which is 0. So from 2 there is an edge to 0. Similarly from box 3 there is an edge to 1, because when you are here you will leave this one and reach this which is 1. So there is an edge from 3 to 1. So this is how the graph construction works. I'm using zero-based syntax system for two reasons. First, this is a circular arrangement and you need to perform circular motion, and when you are using zero-based syntax system you can use modulo to find the next node on which you will land after performing certain circular rotations. So this says okay, perform one circular rotation. Basically this is perform two circular rotation. Why? Because this is leave the next node and reach the next node which is after that. So basically you are leaving two nodes, right? If the value of AI is 5, so you will be performing 6 circular shifts, because you need to leave 5 and then you will be reaching 6th one. So that is why when you want to find the node, the number of the node you would reach, you can do this using modulo arithmetic. So this right here says that you are currently on 3rd and you want to leave you want to leave one node, so you would of course add 2 to it. So you are on 3, add 2 to it, 3 to 5, 5 modulo 4, because n is 4 here, so 5 modulo 4 is 1, and that is why from 3 there is an edge to 1. So basically you can find out the next reaching node using modular arithmetic. All you have to do is in the current position add ai plus 1 and take it modulo n. For this, which was 2 plus 2 4 modulo 4 is 0, that is why there is an edge from 2 to 0. And that is why when I'm working with circular motion, rotation and circular arrangement, I go with zero-based syntax system, and that is why I'm using zero-based syntax system. Enough about that. So here you can see this is the graph, and then how many magic boxes are there? The answer says 4. How? See, this node is a magic box because you can start from here and there is a path which leads back to it, and that path is this. See, you can start from 0 and can come back to 0, and that is why 0 is a magic box. Similarly 2, 1 and 3, all of the 4 boxes are magic boxes, that is why the answer is 4. For the second test case there are only 1 magic boxes. How? This is the graph, this would show you the graph. So in 0 you would add 4, right? Because AI is 3, so you would add 4. So in 0, which is the current position, so there is an edge from 0 to what node? 0 plus 4 modulo 4, which is 0. So there is an edge from 0 to 0, right? So there is an edge from 0 to 0, which is a self loop. Rest edges you can draw yourself. So this is how the test case 2 graph looks like. Now starting from 1, can you reach 1? The answer is no. Similarly for 2 and 3, there is no way you can start from these nodes and come back to them, right? That is why these 3 are not magic boxes, while 0 is. Why? You can start from 0, take this edge and come back to 0, and that is why node 0 is actually a magic box. For the rest of them, for the last test case, this is how your graph would look like, and these 2 would be the magic boxes, because starting from 2 you can reach back to 2 using this path, 2 to 3, 3 to 2. Same goes for 3. So there are 2 magic boxes there, so the output is 2. So this is how we will be modeling our question into. So we'll be modeling our question into graph and then solving this problem. Now the question is how strongly connected components will help you solve this problem. Now if you know strongly connected component, in strongly connected component, if you choose any 2 nodes, there exists a path between them. So if you choose A and B, which belongs to the same strongly connected component, then there is a path from A to B and B to A. Basically there exists a cycle in a strongly connected component. There may be more than one cycle, but there exists at least one cycle. Now if there exists a cycle, then all of the nodes which lie in that cycle are actually magic boxes. Why? Because of course there will be a path which will bring back you to that node itself. So here you see there are 3 strongly connected components, first, second and third. All of the strongly connected components which are having size greater than or equal to 2, like this strongly connected component and this strongly connected component, will have at least one cycle, right? And all of the nodes will be reachable from all of the other nodes. Basically all of the nodes in a single strongly connected component will act as a magic box. So here you can see all of these nodes are magic box, because if you start from 0, you can take, there are more than one cycles in here, but you can take this path and you can come back to 0. So any node which lie in a strongly connected component are part of some cycle, and hence they are magic boxes. So all of the nodes of this strongly connected component will be the part of will be magic boxes, and that is why we would directly add 4 into our answer. Similarly, this strongly connected component which is having size greater than equals to 2, so all of these will be will act as magic boxes, and that is why we would add 3 into answer as well. Now this strongly connected component contains only a single element, right? Now if a strongly connected component contains only a single element, then there are 2 possibilities. First, it contains a self loop. Second, it does not contain any self loop. If it contains a self loop, then this also is a magic box. Otherwise, in the second condition, it is not a magic box. And as we can see here, this does not contain any self loop. There is no self loop from 3 to 3, so this is not a magic box. So there are 4 and 3, 7 magic boxes in total. So all you have to do is find strongly connected component and size of each strongly connected component. If the size is greater than 1, if I show you the code, each time I'm in SCC is a list of all of the node in the current strongly connected component. Before finding the strongly connected component using DFS1, if you do not know, we have already studied strongly connected component using Kosaraju's algorithm, lecture 22 and 23 in graph theory part 1. If you haven't studied these two, I highly advise you to study these two, watch these 2 lectures first, or if you already know Kosaraju's algorithm, that is even better. Now before going to find the next strongly connected component, we are clearing out the list so that SCC contains all of the node in the current strongly connected component. If the size of the strongly connected component, current strongly connected component, is 1 and it contains a self loop, how I'm checking, I'll be telling you in a moment. If it contains if it doesn't contain any self loop, then simply continue, because we can't do anything and we shouldn't add this into our result. Otherwise, simply the size of the strongly connected component, it is added into the result and we are printing the result. This is how I solve this problem. Now if I explain you the code, this is the same code that I have explained in this, the implementation of lecture 23 of Kosaraju's algorithm. So I'm using 2 list for adjacency list representation of graph. Even though each node will have only one edge, so you can actually use a simple array for graph representation, but I'm still going with the traditional way of adjacency list method. So this is to represent the original graph and this is for transpose graph. I have already explained all of these things in lecture 23 when we were implementing Kosaraju's algorithm. This is SCC and order, I have already explained there. This is to check whether the current node is visited or not, and this is the value of all of the nodes, which is basically AI of the input. Value node would store the AI. Now DFS1, DFS is to find out the order. If you remember, in Kosaraju's algorithm, we perform 2 DFS calls. First, to find out the order in which the second DFS order or second DFS function should be called, right? So this is to find out the order of the execution, and this is to find out the actual strongly connected component, right? As you can see, in the strongly connected component, I'm inserting the current node. So basically all of the nodes in the current SCC will be inserted in SCC. So how I'm preparing the graph, the input is given in that form. In this form there are t test cases and then there is n. So there are t test cases. In each test case, what you would do, you would first of all clear all of the input from previous test case. So this is what I'm doing here. Since the REP is a for loop that runs, I've defined it, so using hash define. So this runs from 1 to n. So of course, since I'm using 0 base index system, each time I'm clearing the I minus 1th list. So I'm clearing the original adjacency list and the transpose graph as well. Visited are marked to 0, and also I'm reading in the value. All of the AIs I'm reading as well. So I do not know why it went from here to here. This is a single line. In fact, all of these are written in a single line. I'll be providing the code in the description, so don't worry about that. After that, what I'm doing, I'm constructing the graph. How current position of yours would be current position of yours would be I minus 1, right? Because running a loop from 1 to n. So current node is ai minus 1. So suppose I was finding the edge of this node, so current position would be ai minus 1, and the next position would be ai minus 1 plus the value plus 1, right? And modulo n. So since there is an edge from a to b, in the adjacency list of a I'm inserting b, and in the transpose the reverse edge is there, so in the adjacency list of b you are inserting a. So graph construction is completed. After that, you perform the standard Kosa-Raju's algorithm that I have already explained, and this should be self-explanatory after that algorithm.